So our next installment of the pre-lab videos for the experiments performed in the soil mechanics laboratory is the hydrometer test. This is used to determine the particle size distribution of the fine-grained soils, the soils that are considered fines. Typically, soil solids that are smaller than the number 100 sieve is best utilized in this experiment. We'll talk about the procedure here in a little bit, but this image right here shows that we have multiple jars with soil samples in water solution. The soil particles are in suspension, at least the smaller ones. The larger ones have settled, and you see somebody about to put the hydrometer into a jar to obtain a reading. And we'll talk more about the procedure, but let's first talk about the concepts and background to this test. So the learning objective is simple. We're going to determine the particle size distribution of fine-grained soil solids by hydrometer method. This is the ASTM procedure listed in your book is D422, but there is a newer standard D78 or 7928, and that is basically the same thing. They've just separated it out. So to refresh, obviously soil is made up of an aggregate of lots of different sized particles. The particles, if you were to look at this image right here, you can see that a coarse grained sand is maybe somewhere around 1 millimeter, and the silts and clays are much, much finer soil particles. So it's very difficult to determine what the particle size distribution of the fine-grained soils are, because sieves, the standard practice for separating soil particles utilizing sieve analysis, is very difficult. It's very difficult to make sieves with screening that is small enough to separate the very small fine-grained soils that are about the size of silts and clays. So there's another test that we need. The particle size ranges. If you use the standard classification, ASTO classification, or others, we know that we are looking at the fines in this range right here. And typically the clay fraction of the fines is usually about 2 micrometers is considered that. But fine-grained material is right around 0.075 millimeters, and that's considered the fine-grained soil. So it's important that we look at the distribution of the fine-grained soils in this range. Okay. So to go a little more in detail about what the hydrometer test actually is, we've already mentioned that it allows us to differentiate between silts and clays, but it also gives us the distribution of the fine-grained soil as well. We understand, or we can estimate, that the clays begin at about 2 micrometers, and silts are above 2 micrometers in the fine-grained soil range. However, we have to understand that in order to understand the actual behavior of the soil, we really need to know how much clay is in the material, and it's very difficult to do that with a sieve analysis or a gradation test. So there is a law that we can utilize that allows us to check the time of or the velocity, I should say, of the solid particles that are in suspension of a liquid material, or a liquid in a liquid state. So we mix the soil particles with a liquid or water. Actually, it's a solution, and we shake vigorously until all of the soil particles are in suspension. And then there is a law called Stokes' law that analyzes the velocity at which spheres free fall in suspension, and as that happens, the specific gravity of the solution is changing. So the larger particles will settle first because they are heavier, and the smaller particles will remain in suspension longer. But over time, all of the particles will begin to settle out. It's just a matter of the larger grain particles will settle first, and then the next smaller size, and it goes on from there. And there is a correlation between how much or what size particles are still in suspension over a period of time and the specific gravity of the solution that exists. And if we take measurements of that of the specific gravity of the solution, we can determine what the particle size diameter is that are still in solution, and that will give us an estimate about the particle size distribution of that material. Okay. So as I mentioned, and I'll go over this obviously in a lot more detail when we get to the video of the actual laboratory experiment, but what we're looking at is placing, it says minus 200, really you can go minus 40 material into a beaker with a water solution. The water is not necessarily just water. There is a chemical that allows the particles to separate. Shake vigorously until all the material is in suspension, and then place the jar on the counter. The hydrometer is placed into the solution over various periods of time, over a 24 or 48 hour period, to measure the specific gravity. And then Stokes' law equation is utilized to calculate the particle size and the amount. That's based on the velocity of the free fall of the material. So as you can see in this image here, we start off with all the particles in suspension. We take our first reading at some time t. I'll show you the time frames in a little bit. And notice that the larger particles are beginning to settle out, but the specific gravity has a certain value. At time t2, more of the larger particles are settling and the specific gravity is changing. And then T3 and T4, as you can see, the particles are starting to settle out, and we have a measurement on the hydrometer. And the hydrometer has a standard measurement between 0 and 60, and that is the specific gravity reading. So how does this help us as far as the grain size distribution? And a lot of students get confused on the fact that, well, we do a sieve analysis and then we perform a hydrometer test. Well, I want to make sure that you understand that you can combine the two pieces of information together to create one particle size distribution plot. And that's what we see here in this standard figure that comes from the textbook. But it's important to understand that this range right in here is what we're trying to determine, because in a sieve analysis, we only have information from the number 200 sieve and up. Anything below the number 200 is just considered fine-grained soil. So we can't determine whether or not it's sieve or it's silts or clays. So this is the purpose of this experiment. Okay, so the procedure is fairly simple, and it follows the laboratory manual that you're using. I will say this to start off, as you can see, I'm obtaining the temperature, because what we want to do is we want to look at the viscosity of the material of the water is very dependent on the correlations between the measurements. Okay, so if you look in your procedure in the lab manual, steps 1 through 5 are pretty much done for you. So I'm doing step 6 here, which I'm taking a few readings. So the first thing I'm going to do is in the clear liquid. This is a solution that uses distilled water and sodium hexametaphosphate. That solution is a specific amount of solution. Placing the hydrometer into that to get a couple things. First of all, we want to get a zero correction, meaning it's either going to be positive or negative on that stem. Sometimes it's up to 2 or 3 units on that stem. And then you also want to get something called a meniscus correction. What that's just looking at is you usually read the top of the meniscus in this case, but you want to make sure that the top and the bottom of the meniscus, there can be a correction there. Usually it's about 1 unit. Now what I've done is I've slowly mixed the soil water solution. That's just your soil mixed in with some solution of water and sodium hexametaphosphate to allow the solid particles to separate. And I'm washing every morsel of soil out of that graduated cylinder into the mixing cup there, and that's like a milkshake mixing machine, but it's a specialized cup. I showed you the inside of it with some fins on it. This is specially made for this test. Okay, so make sure you get every morsel out, fill it up to about halfway to to 2/3, not too much more than that, and then the milkshake stirrer is there, and get your timer out. You want to mix it for about 2 minutes at usually low to medium speed is just fine. So you put the cup up and you lift up the upper uh, switch there and then lower it back down, and now the milkshake machine is running. That's how you turn it on. After 2 minutes, go ahead and turn it off by lifting that switch again, but don't just immediately take it out. Make sure you use your water bottle and get all the morsels that are going to be, all the soil particles that are sticking to the stem and the blade of that mixer back into that cup. It's very critical that we keep all of the soil particles together. Okay. Once we have that mixed properly, we pour it straight into the empty hydrometer jar. Make sure again that you get all the particles out of that cup along the fins and into that jar. It's very critical that we get everything out of that cup into the jar itself. So as you can see, that's a pretty easy task to do with the water bottle. Get it all in there because it's mixed up very well, so you don't have large particles typically sticking to the cup because it's been mixed very thoroughly and it's been soaking for quite some time in that solution. That sodium hexametaphosphate breaks up the soil clumps, so they're individual particles. The next thing we want to do is fill up with distilled water all the way to that line, so we have exactly 1,000 milliliters of material in that jar, and you fill it up close to it through the faucet, and then you add a little bit more using the distilled water in the water cup until the soil layer is at the appropriate height. Now you take a stopper, go ahead and twist that on very well, clean it up real good, and then you want to shake vigorously back and forth, and it'll show you this here several times until all the soil is in solution. So you'll see when you tip it upside down that there are particles resting at the bottom because it's already been settling out when you poured it in originally. So you want to shake it up really well, make sure every particle is in solution, and go back and forth. You can twist it, move it around, shake it up a little bit. Just make sure you keep everything in the jar itself. That's why we have the stopper there. So once we're ready, we place the container on the table, twist the stopper off very slowly. Try not to agitate it too much. Begin a timer, and immediately after you place the jar down, take your clean hydrometer and place it into the solution. And you don't want it to bob around too much. You want to try and put it close to where you think the reading will be. Now, some of you have not taken a reading before, so you don't know, but basically you want to avoid it spinning or bobbing too much in the solution. Once you have that, you want to take a reading at the where the top of the soil water mixture is and the top of the meniscus on the hydrometer itself. Okay, and you take readings at the specified time. So it's 15 seconds, 30 seconds, 1 minute, 2 minute. And as you can see, this one is right about 40, 41. And what that means is about 40 or 41. I don't know exactly what that reading was. You'll see it more distinctly when you perform the experiment. But that means you have about 40 or 41 grams of material in solution for 1,000 milliliters of this material at a specific temperature and specific gravity of the soil solids. Okay. After your 2 minute reading, remove the hydrometer, clean it, put it back into the solution until it's about 30 seconds before your next reading is needed, which in this case would be 4 minutes. So about 3 minutes, 30 seconds. Clean it off, dry it, and then put it back in the solution. Don't let it bob too much. Don't let it spin. Let it rest, and then once you get your 4 minute reading or 4 minute time, you take a reading again. Then you remove it and do the same procedure for 8 minutes, 15 minutes, 30 minutes, 1 hour, 2 hour, 4 hour, 8 hour, and then a 24-hour reading the next day. I usually don't do a 48-hour reading on this. It gives us enough information typically. And throughout this, maybe about every hour or so, you do want to take a temperature reading